Welcome back to the deep dive. Today, we're really zeroing in on OpenShift. Specifically, we want to unpack some core concepts, the kind you'll definitely run into with the EX288 certification. Now, maybe you're studying for that exact exam, or perhaps you're just looking to get a firmer grip on Kubernetes and OpenShift generally.
Or maybe just curious how it all works under the hood.
Exactly. Either way, you're in the right place. Think of this as like an efficient way to get the essentials.
Yeah, definitely. And the way we're doing this is by looking at a set of practice questions for the EX288.
Right, with their explanations.
Which gives us a really practical, sort of focused angle to explore these, really important OpenShift resources and commands.
And our mission here, it's not just about reciting answers. We want to pull out the core knowledge from these questions.
That's it, clear, memorable.
And useful right away, no matter your technical background, really. Okay, let's just dive right in. First up, configuration management, always a big one.
Absolutely. So applications need settings, right? Database details, API keys, well, maybe not keys here, but endpoints, things like that. Question 1 starts us off with config maps.
Config maps,
Okay,
yeah.
and it's about how OpenShift handles this kind of, well, non-sensitive configuration data.
Right. The source material makes it super clear. Config maps are the resource for non-confidential stuff.
Environment variables, maybe little config files the app needs.
That sort of thing. And it draws a really important distinction, doesn't it?
It does. Right away, it contrasts config maps with secrets. And this is critical.
Yeah, huge for security.
Because you absolutely do not want sensitive stuff accidentally ending up in a config map.
Yeah.
Secrets are purpose-built for that.
Passwords, tokens, certificates.
Anything that needs encryption and careful handling, keeping those separate is like rule number 1.
Absolutely fundamental. Okay, so we've got our non-sensitive configs handled. Next step. How do we actually tell OpenShift about the resources we want to create? Defining them. Question 2 covers this.
And the focus here lands squarely on the ockapply-f.yam command.
Yeah, the trusty A app apply.
Yeah. So you have your manifest file, the .yaml file, which is basically your blueprint, right? It declares what you want.
The desired state of your object, its settings.
Exactly. And ockapply-f followed by that file name is how you tell OpenShift. Make it so.
And the explanation calls it the most common, the recommended way. It's not just for creating things the first time, is it? That's key.
That's a super important point. Apply is idempotent.
Right. Fancy word, but basically means you can run it over and over.
Exactly. You run the same command with the same file. If the object doesn't exist, it creates it. If it does exist, it checks if anything in the file is different from the current state.
And only updates if needed.
Precisely, which is why it's so good for automation, for GitOps workflows,
Yeah.
Consistent state management.
Makes sense. The question does mention other commands, like create or delete.
Sure, they have their uses. Create will error if it already exists. Delete removes things. Expose creates routes or services. But for that declarative make my cluster match this file approach, apply is your go-to.
Got it. Okay. Configuration stored. We know how to apply our definitions. Now, getting the actual application running and scaling it. Question 3.
This introduces deployment config. And this is an interesting one because it's quite OpenShift specific.
Ah, okay. Not standard Kubernetes then.
Well, Kubernetes has deployments, which are very similar in purpose, but deployment config is OpenShift's enhanced version, you could say. It defines how your app is deployed.
Like how many copies, right? The replicas.
Yeah, number of replicas, which container image to use, the strategy for rolling out updates, like rolling updates to avoid downtime.
Okay. And the source material points out a big advantage it has over the standard Kubernetes deployment.
Yes, automatic rollbacks. This is a really nice feature. If you deploy a new version and something goes wrong, maybe the new pods start crashing OpenShift. Through the deployment config, can automatically revert back to the previous working version.
Oh, wow. Okay, that sounds incredibly useful.
Yeah.
Kubernetes deployments don't just do that automatically.
Not out of the box, no. You typically need more complex tooling or manual intervention. Deployment config builds that safety net right in. Often under the covers, it uses replica sets, just like Kubernetes deployments, to manage the pods.
That automatic rollback.
Okay.
Yeah, I can see how that saves major headaches. Okay, so app is running, scaled, but it's inside the cluster. How do people outside the cluster actually use it? Question 4 tackles external access.
Right, and this brings us to the ingress resource. Think of your OpenShift cluster network as sort of internal.
Detected, yeah.
Ingress acts as the traffic controller, the entry point for external HTTP and HTTPS traffic. It directs requests to the right service inside the cluster.
So it's like the front door that knows where everything is.
Pretty much. And it's smart. The explanation mentions it can route based on things like the URL path.
Oh, right. Like app 1 goes to one service, app 2 goes to another?
Exactly. Or based on the hostname requested. And another key thing it mentions is SSL termination.
Okay, break that down. What's the benefit of SSL termination at the ingress level?
So instead of each individual application needing to handle the complexity of HTTPS, managing certificates, encryption, decryption.
Which can be a pain.
Right. The ingress controller can handle it all centrally. It terminates the secure connection, meaning it decrypts the traffic, and then can forward plain HTTP traffic to your internal services if you want.
Oh, so it simplifies things for the apps themselves.
Hugely. They just deal with regular HTTP internally, while the ingress ensures secure communication with the outside world.
Makes a lot of sense. Ingress, the smart, secure front door. Okay, next challenge, data. What if our app needs to store stuff that, needs to stick around, even if the pod restarts or gets moved? Persistent storage, question 5.
This is where persistent volume claims, or PVCs, come in. A PVC is essentially a request for storage made by an application or a user.
So the app says, hey, I need some disk space.
Kind of, yeah. It says, I need storage with these characteristics, like maybe a certain size, or it needs to be accessed in a certain way. Read write once, read write many.
And the source links this to storage classes. What's that connection?
The storage class is crucial. Think of it as defining the types of storage available in the cluster.
Like different tiers. Gold, silver, bronze storage.
Exactly like that. One storage class might map to fast SSD storage, another to slower, cheaper magnetic disk, maybe another to cloud provider block storage with specific features.
Okay.
So when you create a PVC, you typically specify which storage class you want. OpenShift then uses that storage class definition to dynamically provision the actual underlying storage, the persistent volume, PV.
Ah, so the PVC is the request, the storage class is the template for what gets created automatically.
Precisely. It abstracts the underlying storage details away. The developer just asks for storage via a PVC referencing a storage class, and OpenShift handles provisioning the actual PV based on that class.
Got it. Dynamic provisioning via PVCs and storage classes. Okay, shifting gears a bit. We need to keep an eye on the cluster itself, right? How much CPU and memory are being used? Question 6 looks at monitoring resources.
Yeah, absolutely vital. You need to know if your nodes, the actual machines running your pods, are getting overloaded. The command highlighted here is awk-add-m top nodes.
Awk-add-m top nodes. Simple enough.
It's a really direct way to get a quick snapshot. It shows you the current CPU and memory usage for each node in your cluster.
So run that command and boom, a list of nodes and how busy they are.
Pretty much. It gives you the raw numbers and often percentages of usage. Super useful for spotting if a particular node is under stress.
Right, for capacity planning, troubleshooting performance issues.
Exactly. Finding bottlenecks, seeing if you need to add more nodes or maybe figure out why one node is working much harder than others. Basic but essential health check.
It's perfect sense. Okay, we've talked about access from outside, storage inside. What about controlling who can do what within a specific part of the cluster? Question 7 gets into access control, specifically within namespaces.
Right. Namespaces are key for organization in OpenShift, like virtual boundaries within the cluster.
So you can separate projects, teams, environments.
Exactly. Provides isolation. Now, within a single namespace, how do you control permissions? That's where roles come in.
Okay, a role.
A role defines a set of permissions like what actions, get, list, create, delete, are allowed on which types of resources, pods, services, config maps. Crucially, a role is namespaced. It only applies within the namespace where it's created.
So a role is like a job description within one specific department, saying this job allows you to read pod info and update the config maps, but only in this department.
That's a great analogy. And then to actually give someone that job description, you use a role binding.
Ah, the binding connects the role to a user.
Exactly. A role binding associates a user or group or even a service account with a specific role within that same namespace. So role defines the what, role binding defines the who gets those permissions, all scoped to one namespace.
Got it. Role for permissions, role binding to grant them, both tied to a namespace.
Ah.
Okay, now you mentioned service accounts there. Let's pivot to the applications themselves. How do they identify themselves when they need to interact with OpenShift? Question 8.
Yeah, this is where service accounts become important. It's not just human users who need identities. Applications running inside pods often need to talk to the OpenShift API server, maybe to discover other services or read configuration.
So the app needs its own username and password, kind of.
Sort of, but specifically for processes. A service account provides an identity for applications running within the cluster. It's automatically created in every namespace, and pods use its associated token to authenticate to the API server.
So it's an account for the application, not for a person.
Precisely. And this is crucial for security and access control for your apps. You can grant permissions to a service account using roles and role bindings, just like you would for a human user.
Ah, okay. So you can control what an application is allowed to do within the cluster using its service account identity.
Exactly. Principle of least privilege again, but applied to the software itself.
That makes total sense. Okay, we've looked at individual pieces, apps, storage, access. What about the big picture? The overall health of the entire OpenShift cluster? Question 9.
This points us to the get cluster operators command. Think about OpenShift. It's not one single program. It's a complex system made of many different components all working together.
The control plane, networking, storage integration, registry, lots of moving parts.
Exactly. And cluster operators are these special controllers that manage the lifecycle of these core OpenShift components. They make sure things are installed correctly, configured properly, and stay running.
So when we run a cluster operators, what are we looking for?
You're mainly looking at the available, progressing, and degraded status columns for each operator. Ideally, you want everything to be available. True, progressing false, and degraded false.
Meaning it's running, not currently changing, and not broken.
Right. If you see an operator marked as degraded true or stuck in progressing true for too long, that's a red flag. It means a core part of your cluster is having problems and needs investigation. It's a high-level health check for the whole platform.
Like checking the vital signs of the entire OpenShift system. Got it. Finally, question 10 brings us to upgrades. Big operations. What's absolutely essential before starting an OpenShift upgrade?
The explanation is crystal clear on this. You must confirm that all your cluster operators are healthy before you begin.
Going back to that awk get cluster operators command we just talked about.
Absolutely. You need to run that and make sure everything shows as available and not degraded.
Why is that so critical before an upgrade?
Because an upgrade is a complex process that touches many of those core components managed by the operators. If a component is already unhealthy before you start, the upgrade process is much more likely to fail or make things worse.
You're basically trying to perform major surgery on a patient who's already unstable.
Exactly. You need a stable, healthy baseline. Healthy operators mean the cluster is in a known good state, significantly reducing the risk of the upgrade going sideways. It increases the chances of a smooth, successful upgrade dramatically.
That makes perfect sense. Check the vitals, ensure everything's stable before you attempt the big procedure. Vital takeaway.
Definitely.
Wow, okay. We've really covered a lot of ground there, all stemming from those 10 practice questions. Config maps for non-sensitive config.
Config apply for managing resources idempotently.
Deployment config for app deployment, especially that rollback feature.
Ingress for external access and SSL termination.
Persistent storage using PVCs and storage classes.
Monitoring node resources with AGADM top nodes.
Access control within namespaces using roles and role bindings.
Service accounts giving identities to applications.
Tracking overall cluster health via OpenShift. Get cluster operators.
And that critical pre-upgrade check for healthy operators? Q.
Yeah, that's quite the list. But honestly, these 10 really do feel like the foundational blocks for working with OpenShift, wouldn't you say?
I completely agree. If you can get your head around these concepts, you're in a really good position. Whether it's for the EX288 exam, just doing your job day to day with OpenShift, or building that solid knowledge base.
Understanding these pieces really pays off immediately.
Definitely. They touch on configuration, deployment, networking, storage, security, monitoring.
Yeah.
It's the core stuff.
Yeah, absolutely. And maybe a final thought for listeners as they digest all this. Think about how these pieces interconnect, How does a change in a config map potentially trigger a new rollout via deployment config? How does a role binding applied to a service account affect what that application using a PVC can actually do?
Yeah, it's all linked. Understanding those connections is where the deeper mastery comes in. Which area maybe feels most relevant to what you're working on right now? That might be the next place to dig even deeper.
Good point. It's a fascinating system when you see how it all fits together.